from the Department of Chemistry, a professor in the Department of Chemistry. So he's graciously agreed to show us the chemistry side of what he does. And so we welcome you, Dr. Mandal.
Thank you. Thank you so much. Well, good afternoon again. This is my second talk to the ASCEND program. I think Christine knows very well that I also gave a talk on some of the application of organometallic complexes, particularly on breast cancer. I'll touch base on that one a little bit, and then I'll talk to you about some of the other stuff we did after that. So, excuse me. So this slide shows some of the cancer facts. So I just want to tell you something about, we are working on rhenium compounds. We cannot take drugs. We cannot tell them drugs because they are not in the drug stage. So we are working in the area of rhenium chemistry, and we found that they are very interesting. They have numerous properties. One of the properties has to do with anti-cancer. And it is known that these couple of compounds like cisplatin and other derivatives, or you can say that other related platinum compounds, they are very important anti-cancer drugs. Almost they are used for any kind of cancers, like particularly for testicular, ovarian, and obviously for other cancers. So all of these platinum or whatever other these cancer drugs, they have severe side effects, and they also have problems with drug resistance. So people are frantically looking for alternatives, and since you can see this one, in this one, transparency periodic table, platinum is pretty close to rhenium. So one of the alternatives for the platinums, there are other metals like iridium, osmium, people are trying, and they are encouraging one, but a lot of work has been done on rhenium. But this is same, it can fall under the category of heavy metals, just like platinum, okay? So we did some of our work earlier, and these guys, they in their review article, they gave our accounts of our work, and this is the particular part of that our work actually. I'm not going to talk about that, but I just want to tell you that some of our work published in a review article by these folks. And as I said to you, that I just presented our work earlier, anti-cancer stuffs. This is the one published in the molecular cellular biochemistry, and all of has to do with this what is that called, breast cancers, and two different breast cancers, like hormone dependent or hormone independent. And we have an account of almost 100 compounds, and how do they behave with these cancers. I already actually talked about that. So now I want to tell you, summarize some of these things in this transparency, that the one I just now told you, that this hormone dependent MCF7 has been seen that by this compound RPR2 and other compounds like TOS7, PR7, and all these compounds except this one, TOS7, all of these have rhenium atoms, but two rhenium atoms. As you can see here, all of except this guy, TOS7, all of them have two rhenium atoms. So I'll talk about that. I'll tell you something why A2 is good or bad. I'll tell you. But our lab is trying to make varieties of complexes with rhenium, whether it's a 2 rhenium or 3 rhenium, it doesn't matter. So we are trying to make complexes. So this is the one part of my earlier PhD student TJ. I think many of you know him actually. That was part of his PhD thesis, the TOS7. And as you can see that IC50 are remarkably low in all of these things. Actually, they are this is in the low nanomolar range. And you can see that this one also has these things, PR7 also has, and these are also comparatively very low, less than 1. It's very encouraging, as you can see. And if you think about the normal cells, they are not that bad compared to the cancer cells. So this is the thing actually. We did some of our work at University of Maryland by my collaborator. And they did for this one and this PR7 or PR2. But some of our work on, this is the hormone independent, particularly TNBC, triple negative breast cancer cells, are shown shown in these slides. As you can see that these are all, practically all of them are TNBC cell lines, all of these, except HeLa one. But you can see that they are remarkably good anti-cancer agents, particularly PR7 among all these things. And you can, we did the only thing, as I can say to you, that previously these are all 2 rhenium complexes. If you see this, I tabulated the IC50s for all of these. You see that this is the PR7 among these. This is the PR7 is this molecule PR7, 2 rhenium atoms are there. These are really extremely good among all of these things. 0.37 micromolar. I mean, it's a very low nanomolar range. It's extremely good. Even for this another one pretty known this TNBC cell lines, MDMB 453.2, and this one is 0.4. It's extremely low. And also, as you can see in the case of HeLa, it's also extremely low, IC50. Okay, and the thing is that only thing I can tell you that all of these compounds has to do with 2 rhenium atoms. This is the pardenate one, and this is the pardenate, and other stuffs are not pardenate. They are bridging compounds, 2 rhenium atoms are there. And it was, see that how does it work on cell side distribution? It does not, it looks like it does not target mitosis or cause DNA damage. So then if you think about that one, I just told you these IC50s, and if you compare with these known breast cancer cells, breast cancer drugs like tamoxifen, for the MCF7, it's a 16.2, and this is MCF7. MB231 is 13 micromolar, but ours is, as I said to you a minute ago, that it's a way low, as you can see, all of these. Okay, so that's the comparison I put, that this is the known, drug, breast cancer drugs. All of you know that one. So that's why I want to point out that one. Then we did several of our compounds. These are mostly, you can see that these things are, many of them are actually 1 rhenium atoms, like this NIC7, IV6, this DOS7, many of them are 1, but still compared to this known anti-cancer, IC50 for anti-cancer drugs, these are not very high compared to that actually. So you can see that these are the 3 cell lines, OPCAR8, Kuramushi cell line, and the OPCAR4. All of them are really acting, they are compared, this PR7, as you can see, that way low, actually 792 nanomolar. So it is actually always, you can see this one, all of them. PR7 is always the winner. For some reason, we don't know for what reason, it's extremely low IC50. And this is the PR7 structure, as you can see. So almost all of them have the similar structure, like NIC7, this thing you have only nicotinate is there, but it's only pardenate is there. But others also, these groups are changed, but everything else is same almost. 7, 7, you can see this one. So structurally they are very similar, but for some reason, PR7 is working very good. So this is about our work on ovarian cancer. Then this is the one we did for colon cancer study. And these are the two cell lines. These are resistant cell lines, actually, HCT116 and HT29, resistant cell lines. And we did for the things like 1 rhenium and 2 rhenium atoms there. So the compounds, we assigned them as PR6, PR7, ASP7, RPR1, RPR2, ASP6. So you see that PR6 and PR7, they actually work much better than any of those things. Here, you see that, excuse me, this one, the white one is 1 micromolar, the other one is 10 micromolar, 100 is the other micromolar. That's not micromolar, I'm sorry. This one was done with microgram per milliliter, but the thing is almost same except 1/2 of that. So if you convert this one, it should be 0.5 micromolar, 5 micromolar, 50 micromolar actually. So anyhow, so I can tell you that this works, PR7 and PR6 works very good on these resistant colon cancer cells. This, I think, one thing I want to tell you that this one is the current drug for colon cancer. One of the drugs, you can PUOX. It's a 5-fluorouracil oxaliplatin mixture. Okay, it's a mixture of 5-fluorouracil and oxaliplatin. And as you can see, compared to that, all of our compounds are extremely doing very good. Okay, so I will just show my next slides that how really it compares with the PUOX and other one of our compounds like PR7, the best one. So next one, as you see here, you can see this. This is the one PR7. This is the dose response graph. I just put it here. PR7, on the x-axis molarity is given here. So you see that PR7, if you compare the effect, PR7 and 5-fluorouracil or 5-fluorouracil oxaliplatin mixture, it's much better than that. And if there is synchronization, if you mix this one with PR7, okay? So it may be possible to design a drug instead of the PUOX. It could be PUOX and PR7. It will do a great job, as you can see here, okay? So let me show the next one. This is now, I'm coming to this pancreatic cancer disorder. The pancreatic cancer research, as you know that once we came here, actually this was accidental, but what I want to tell you that these are the known drugs for pancreatic cancer. Folfirinox, there's a mixed folinic acid, uracil, and irinotecan, oxaliplatin, then gemcitabine, cisplatin. It's a mixture of those actually are used. And off is oxaliplatin, 5-fluorouracil, folinic. These are the current drugs for that actually. And this is not curable, as you know that one. So, but these are possible drugs. And I'm going to compare how our rhenium compounds actually acts on these. So this is one of the rhenium compounds, PR4. On this is, we have taken two cell lines. One is BXPC3, and the another one I'm going to say to that one. This is you see that PX. You see IC50 for this one using this PR4. This is the same series of PR7 and PR6, almost the same, except in this position, this 5 and this is 2, 9, this is 3, 4, 4, 7 position, 2 phenyl groups are there. It's almost same. So here you can see the IC50 for this one is about 2.5 micromolar for this particular one, this PR4. And then once PR6, this is the PR6 one is a very similar one, but two phenyl groups are there, and that also has a very low, not extremely low, but low micromolar range actually for the IC50. Then I just want to say to you the another one about. I'm sorry, just 1 second, please. This is the one I didn't talk to you about that. This is the PR6 compound. Cell line is different actually. I put you the other one BXPC3, but this is L36PL. This is the stem cell line, and then this is a resistant cancer cells. Okay, this is one of the worst cancer. Actually, you can have that this cell lines. So that one, and then it came to RPR. It's a kind of compound, not really our the one what we are doing, like all of this and nitrogen containing, but in these things I have phosphorus, as you can see, phosphorus. But one thing I want to tell you that we still have the same multi-pardenate group we have here. Okay, how does it differ? But that one, these two instead of amines, these are phosphine ligands are here. But as you can see that even that is changing that one, these things are highly active on these cell lines, and it is this one is almost 0.5 micromolar actually IC50 for this one, this RPR1. Then RPR2 is the same as that, actually almost the same. This is the only one carbon extra. It's only one carbon extra. If you put that RPR, it comes, RPR2 comes. And why did that one? That way solubility, it will be more soluble, meaning it will be more lipid soluble. That was the idea to add this one. And you see that that is much better than the previous one, what I said to you. So it says that one, most likely solubility is one of the very important things. Probably the membrane, cell membrane to cell membrane, the compounds can easily pass through. And then the next one is RPR3. It's not that good, but it has 4 carbon atoms you have here. But where you have 3 carbon atoms, that works pretty good. All right, so this is one of the another compound. This is the, we call ASP6. This is aspirin moiety is here with this our rhenium compounds. So you can say that 2 drugs together put almost aspirin and our rhenium compounds. So that's a complex compound we got, and we treated with another cell line BXPC3 72 hour actually, and IC50, as you can see, it's less than 2.5 micromolar. Then this is one of our best compounds, and we tried this. This is I told you in the very beginning that we worked on rhenium complexes where 1 rhenium, 2 rheniums, and 4 rhenium complexes are there. This is one of the complexes we accidentally synthesized. I mean, it came while we were doing something, we got this compound and we crystallographically characterized. So it is all characterized, and this is the paper. It was, it's in preprint stage actually, didn't get time to publicity yet. But I want to tell you that this has if you see this one, IC50 is less than 0.25 micromolar. That means it's the best among whatever I did research. That's the best compound. But I didn't tell you the worst part of this one. This one is this this compound I cannot make anymore. I did it here. I cannot make it anymore. I wanted to do more studies. I could not do because I don't have any more. And I cannot synthesize that one. That's the worst part of my research, actually. For some reason, it doesn't work anymore. So, and also the another thing is that we did not for pancreatic cancer, but we did for breast cancer. This is also the best drug among best compound among in the breast cancer one, like MCF7 and MDA, MB231. That's the best compound in terms of anti-cancer properties. But the problem is that this is toxic too. I mean, MCF10, it also very toxic too also. So although it's a very less one. So my understanding is that one, and I also saw comments from other researchers. It is probably, if you introduce more of rhenium, it becomes more toxic. The rhenium compounds are actually not so toxic. I mean, it has been seen, and they are tolerable, much better than other heavy metal like platinums and other things. Rhenium is very tolerable. But then for this particular thing, 4 rhenium atom, I mean, it's very toxic on normal cell. So my next thing I want to talk to you about another kind of research, another cell line. I want to talk about that. This is the skin cancer one. This is the we did on melanoma cells, and this group of compounds. This is one group of compound, not with other stuffs actually. It's ASP. This is the aspirin stuffs. Actually, this was done by my a long time ago by my undergraduate. I think some of you know, probably Christine might know. Her name is Paula Olczak. So she was doing PhD at Johns Hopkins. I don't know what she's doing right now, but that is her work. ASP compounds. So we synthesized this 8 compounds of and we found out that the thing is that ASP7 is least, you know, that all of these things, what we saw 7, PR7 or whatever 7 you saw, that one, they are the best. But in the case of this one, this the melanoma cells, this is the worst one. For some reason, we don't know, okay? So thing is that, as you can see for ASP4 is which one? It come probably this one most likely, ASP4. So that's the best one, okay? For some reason, then structurally, ASP4 is where, let me show you one of these structures probably. Here, excuse me, the 4 meaning this 2,9 dimethyl position. This is the phenantholyl ligand 2,9. All of these 4s has this methyl groups are there. So why I'm telling you that one, I will tell you that some other melanoma cells, how other group of compounds work. So this is the thing actually work best, and it's the IC50 is pretty close to 5 micromolar, as you can see. The worst is SP7, but others work between 10 to 25 micromolar. Okay, and my last one is the A375 cells. It has been seen that this is a different kind of compounds. Actually, CH, this is chloride, actually, chloride thing instead of aspirin or other thing. These are chlorides, all of these. And for some reason, again, I said to you that 4 is working very good, and you can see that 4 is working very good here. So it has to do with the methyl group for some reason. But in this case, 7 is working also very good. Okay, for that, for what reason we don't know. So that's the thing actually I wanted to tell you about the anti-cancer properties, what we are studying here at Morgan. These things, I already did some of my work with prostate cancer. We published a book chapter long time ago, maybe 15 years ago. And I don't work anymore on prostate cancer, but on these things. So after doing all these things, it may be worthwhile to discuss a little bit of mechanism. How does it go actually? PR7 is the best one. So we are doing exploring mechanism, but not anywhere right now to tell conclusively anything. But want to tell you that we did one of these things, UV visible spectroscopic study, DNA titration. It is known that, most of the drugs, somehow they interact with DNA, they bind to DNA. So we tried to study the DNA binding properties. And this is the one I want to talk about, the UV spectroscopic study for the PR7, because that's the best one. So I want to talk to you about that one. So this is the UV titration, and we added, as you can see, that these are the things we added this amount of DNA, and we observed what kind of this absorbance you are getting here. Okay, you see that although it's hard to see from your end, but it is. I can tell you that there is a, if you take this thing, that this is the bottom one, or so it is. There is a this absorbance, and this wavelength is actually little lower than this one. That means we call this one, when it happens, it's called hypochromism. Okay, so this one shift little bit to the right. Okay, so that's called bathochromic shift. So this one, you see that there are two things are there, bathochromic and red shift. That if it happens when you do the titration, DNA titration, generally we ascribe as due to the what is that called? It is binding. The complex is binding to DNA through intercalation, we call it. Okay, if you have this this drop of absorbance along with the shift to red shift to the wavelength, we call it, if it happens, we call it as intercalation. On the other hand, if you see this one, this is the one you see the, but in the case of visible region, this is UV visible region, this is called DD transition, you call it here. You see here, it's a lower absorbance, right? So this one is the or one of these high, so it's going to higher absorbance. Also, it's going to the right side, meaning what should I say? Wavelength. It's a bathochromic shift. Okay, so if it happens, we call that one. It's not. We call hyperchromic effect. Actually, this one. So it is. It looks like one mechanism is involved here, another one is here. Also, I did not say to you this one. If you see this, all of these absorbances are actually dropping, but they do not shift to higher wavelength or no bathochromic shift. So for this thing, we generally ascribe to this one as what is that called? DNA binding is there, but this is the one, it binds to minor group of the DNA. So one mechanism is minor group, binding to minor group. The other one is intercalation. The other one is different mechanism. So it seems that the compound is conclusively cannot tell that it binds to DNA to intercalation. Okay, it binds to through many other mechanisms actually. So it's very premature to say anything right now about this, but these are our preliminary finding about this, and we did for other studies with many other compounds like emission and other things like cycle voltammetry, also viscosity studies. It seems that the compounds bind to DNA, but we don't know how do they bind, meaning whether intercalation completely, or this one DNA minor group, or DNA major group. In fact, why I'm saying that DNA major group, we did some docking study of a compound and it found out that our compound binds to the DNA minor group. So many of these things are possible, but we cannot conclusively tell what's going on, what kind of binding it does to the DNA. Well, that is our conclusion about our study I'm doing right now on this. So if you have any other question, you can ask me about that. But let me tell you that who are the guys involved in the project. I had numerous undergraduate and graduate students. They were involved. None of them are here right now, involved in the project. And these are my collaborators. David Weber in this University of Maryland, Baltimore. Paul Shapiro, he is the chair of the pharmaceutical division at University of Baltimore, who did in fact, this one, what is that called, the melanoma study. These three guys are University of Wayne State University School of Medicine, President Sarkar Majumdar. And this person, probably many of you know her. Actually, Christine knows her, I'm pretty sure. She was invited to give a talk here, and she did many of my triple negative breast cancer study. This person is at Indiana University School of Medicine, and you know that Dr. Wachira, he was the person how to do cell culture, how to do heat, taught me everything. And Dr. Mara is extensively doing on my project. In fact, I'm supposed to submit a paper. It's already, everything is ready. For some reason, it's there. So she did the what is that called, apoptosis studies of my one of my compounds. And Dr. Pramanik, he is helping me also doing a lot of biological studies. I thank you all for listening. If you have any question, please feel free to ask me.
Thank you, Dr. Mandal. That was very interesting. So if anyone has questions, just unmute yourself and ask. I wanted to ask, when you do the DNA binding, what kind of DNA do you give to it?
CT, cup thymus DNA.
Okay. So would it be different if you gave, like, I don't know, do drugs just bind anywhere? But you said this one binds to the minor groove.
In fact, majority of my compounds, all of these 150 compounds I did, majority of them binds to DNA minor group. Not intercalation, not DNA major group, or any other things I can see. It's a DNA minor group, all of these. In fact, the one I will be submitting the paper with you, that is, I have seen that one. It's all of the compounds are DNA minor group.
Okay. And then you don't have cell lysates for when you treat these compounds to the cells. Do you have any cell lysate that people can test?
I actually got some cell line from Texas. This one of these important these pancreatic cancer cells. I don't know still they're alive or not. I put in the refrigerator and a lot of things have been done. Actually, I really don't know whether still they are there. But I got as a donation from there because I was looking for my grant proposal. They said that you need to do this one. This is the cell. It's a stem cell, and you need to this resistant pancreatic cancer cell. I got that one. I never got a chance to do that one. And a lot of things happened during the last 2-3 years, right? So I might have lost that one. It may be there, but I doubt it.
Okay. Any other questions?
Well, thank you so much for listening. I really appreciate. If you have any question, you can email me about my research. I really appreciate all of you for coming to listen to me. Thank you again.
Thank you. And I'll send a student to you because I have a student who seems to be interested in cisplatin.
Okay, sure. Thank you. Thank you so much.